Welcome, my name is Lutz Warnke. Today I'm going to talk about a topic which lies at the intersection of enumeration and probability, and all this is joint work with Bill Correll from Maxar Technologies and Chris Swanson from Ashland University. So what are the objects of interest for this particular talk? So the objects of interest for this talk are so-called Costas arrays, which for the moment I just want you to think about as permutation matrices which satisfy some extra structural constraints. Okay, so the topic of studying discrete structures with extra constraints is a very classical one. So if we think about, for example, graphs with certain constraints, then we can study things like planar graphs or triangle-free graphs and so on and so forth. And here we're doing the analogous question in the context of permutation matrices, just that here, the particular constraints we're going to look at do not arise maybe from a combinatorial perspective, but they come from some engineering applications. In particular, they have their origins in radar and sonar research from the 60s. So these are real-world constraints that people actually care about. And so whenever we are exposed to some new objects, the first question we typically ask, okay, what properties do these objects have? And so in this case, one very classical question is, okay, how many are there? That's the kind of the question we want to pose here. And the main message of this particular talk will be that we get some good upper bound on the number of these Costas arrays. In particular, we're going to resolve a well-known conjecture in the area, which concerns how many there are in relation to the total number of permutation matrices. Okay, so the result I want to talk about is basically of the form: if we take the total number of n times n Costas arrays and divide it by the total number of n times n permutation matrices, then we want that this is exponentially small. It's e to the minus constant times n for some absolute constant c bigger than 0. Okay, and the way to think about it is that you can just think of all n times n permutation matrices, you put them all in a bag, and then of this bag you choose one uniformly at random, and this quantity is basically telling you what's the probability that a randomly chosen n times n permutation matrix actually is a Costas array. So that's this fraction that we want to attack here. So now that we've seen what are the objects of interest and what is the main question, you might ask, okay, why should we care? So first of all, I think the question that we want to enumerate these objects is an extremely natural one, in particular so because the constraints that we are dealing with here on these permutation matrices, they're not just some toy examples or some simplified constraints, but they're really the ones that actually appear in practice. So I think that's very appealing that these are like real-world constraints that people actually care about. And maybe a third motivation is that this is, as we're going to see, really a nice test bed for probabilistic tools that we can try to apply here. And I think there's also a lot of potential here for applying more analytic or enumerative tools as well, as I'll mention in the open problems. Okay, so let me maybe just dive straight in. What are actually these Costas arrays? So as I mentioned, they have their origins in some classified Nazi research in the 1960s. The goal of improving the performance of certain sonar and radar technology. So mathematically, what these are certain permutation matrices, and they satisfy an extra property that all vectors between different ones are distinct. And so I think this is one of these definitions where it's easier to see non-examples, to see what are not Costas arrays, and then I think the concept will become clear. So here on this right side, I depicted 3 permutation matrices which are not Costas arrays. Okay, so let's start here in the middle. This example. So here you see you can connect these 2 ones, you get a certain vector, and this vector actually coincides here with this second pair of ones. Okay, so the fact that between here and here you can draw the same vector, that violates this Costas condition. A similar remark applies here. Here we also can draw a vector between these 2 ones and these 2 ones, and they will give you the same vector. So again, this is also not a Costas array. The third kind of situation you can think of looks more like a parallelogram. So here we can also draw the vector between these two ones, and it gives exactly the same vector as these ones. Okay, so also not a Costas area. And I invite you to check that in this 4 times 4 permutation matrix, all the 6 vectors between these two pairs of ones and so on, that they're all distinct. Just take my word for it that this is true in this example. So this constraint here, that all these vectors are distinct, it might appear on first sight maybe not so combinatorial. So maybe you want to interested. So where does it come from? How is it used? And so the simplified story is that you can imagine that you want to use these Costas arrays to decide at which times and which frequencies you want to send out your sonar pulses, for example. So here, maybe the columns determine the time and the rows determine the frequency at which you send out certain pulses. And the key point is now when you send out these pulses, then these pulses get reflected. And depending on the distance of the object and the speed with which it moves, this will lead to a shift of the time and the frequency. Okay, so the time the time shift will depend on how far the object is away, and the frequency shift will depend on the speed of the object. And so now when you get these signals back, when you get these active signals back, you want to figure out where's the object. And here, this key combinatorial property of Costas arrays comes in very handy, because if you have a shift of time and frequency, okay, which corresponds to some shifts of the ones here in your permutation matrices by rows and columns, then the key property is that a shift of time and frequency can never make any two ones coincide here in this corresponding matrix. Okay, so this is, of course, if you only wanted to make one of them coincide, that's always trivial. You can always shift two ones to make them equal. But the key property here is any shift cannot make any two of them equal. And the key point is somehow that in this radar and sonar application, because the signals that you get back, they correspond to shifts of time and frequency, by this key property, you can kind of really figure out where's the object that I'm interested in. Okay, so maybe that's all I wanted to say here about the motivation. For us here, from a mathematical perspective, what is the quantity of interest? So what we're going to be interested in is the number of these objects. Okay, so we're interested in the number of n times n permutation matrices that are Costas arrays. Okay, so let me say a few words about what is actually known about these objects. So right from the beginning, people were interested in questions like, okay, do these objects actually exist? And this was answered in this very nice paper by Golomb and Taylor in 1984, where they showed that indeed for infinitely many n, we know that at least one Costas array exists. Okay, so these constructions are algebraic in nature, so it only works for certain numbers n, which satisfy certain number theoretic properties. For example, if n is a prime minus 1, then this algebraic construction works. I think some variant also works for n for prime minus 2, and so on and so forth. But we know for infinite subsequence of n, these guys exist. And in fact, if you look into how these algebraic constructions work, you can even figure out that there's at least some small polynomial many, maybe roughly quadratically many. Okay, so that's what's known. It later actually turned out that in disguise, in some proof, similar constructions were also considered by Gilbert while in the context of so-called studying Latin squares. Okay, so this here is what we know about the lower bound. For infinitely many n, we have some polynomial lower bound. So what about the upper bound? So in this paper by Golomb and Taylor from 1984, they immediately asked the question, okay, what can we say about upper bounds? In particular, to get started on this problem, they suggested, okay, let's maybe show that the number of Costas arrays divided by n factorial, the total number of n times n permutation matrices, that at least this quantity should go to 0. And this was one of their the problems they listed there in this paper as one of the 10 fundamental open problems. And this received quite some attention in the 80s. There were 3 independent proofs that emerged, each using the second moment method. and each of them giving this polynomial decay. So they do not only show that this number of Costas areas divided by n factorial tends to 0, but they actually show the decays of something like the most order 1 over n. So it actually goes polynomial to 0. And as I mentioned, this was in these 3 independent works, one by Benjamin Weiss from Hebrew University. Some of you might know him. He's the advisor of a Fields medalist Lindenstrauss. Then another proof was given shortly after by Victor Reiner independently, who's now a full professor at Minnesota. And another proof was given slightly later by Hugh Davies, who's an electrical engineer. Okay, so that's where things were standing for a long time. We have this, first of all, huge gap between upper and lower bounds that we can prove theoretically. And moreover, you know, in the 80s and 90s, there was a lot of effort in actually trying to enumerate these, the number of Costas areas precisely, partly motivated by the fact that, you know, if you enumerate all small n times m Costas areas, maybe you can see a pattern that allows you to generalize this pattern to larger n. And on the other hand, also for certain applications to fine-tune certain parameters, it's also useful to know what this number of Costas areas actually is. But the upshot was that when people studied these numbers C of n for small n, they observed that this upper bound, you know, that it decays like order 1 over n, this polynomial decay, that's certainly not the truth. They observed that the decay is much steeper. And so that's why this focal conjecture emerged in the late 80s, that this actually gives some exponential decay rather than some polynomial decay on the density. And so when Drakakis updated this survey by Golomb and Taylor around 2011, he really said that this is one of the core theoretical problems in the domain here of this Costas areas, that we really want to show that the density of Costas areas among all permutation matrices decays exponentially. And this is exactly what we showed here in joint work with Bill Correll and Chris Swanson. We indeed showed that this quantity decays exponentially, so we have some explicit constant c bigger than 0, so the number of n times n Costas areas divided by n factorial is at most e to the minus this constant times n. Okay. Again, the intuition is that this means that if you select a random n times n permutation matrix, what is the probability that it is actually a Costas area that decays exponentially? Okay, so this verifies this core theoretical problem that can be traced back to these folklore speculations from the 1980s. So whenever we see such an upper bound, the first thing we probably ask ourselves is, how good is this bound? Is this bound best possible? Let me first just comment here on this fact that here we have n at least 3. So, so strictly speaking, this is needed for the statement to be true, but for the trivial reason that for n equals to 1 and 2, simply all n times n permutation matrices are Costas areas, so this density is trivially 1. Okay, so this n at least 3 is kind of like a non-assumption. But what about this exponential decay that we have here? Well, we know that for infinitely many n, these Costas areas exist, right? So for these n, we know that C of n is at least 1. So this fraction is certainly at least 1 over n factorial. And so this is happily at most n to the minus n. So in other words, we get a lower bound of e to the minus n times log n. Okay, so if you compare this, we have decay here linear in n. Here we have decay lower bound n log n. So up to this logarithmic factor here, our decay is actually best possible. Okay, and as I of course mentioned, closing this gap between this lower bound and this upper bound, that's one very interesting open problem. So our proof here will be probabilistic, and what I find very interesting about it is that we're actually going to use some proof ideas from random graph theory that can be traced back to some breakthrough result of Bela-Bolobash on the chromatic number of dense random graphs. So somehow some idea that was useful for studying the chromatic number will turn out to be useful also for getting this exponential decay bound. And this is something to do with that in the end we want to apply a certain concentration inequality, and in this work Bolobash introduced some very nice trick and insight how to overcome certain technical difficulties. Okay, so on the next slide I want to give you a quick glimpse into how we actually prove this upper bound of C of n over n factorial is exponentially small. So what is the basic idea? So the basic idea is, first of all, of course, we somehow need to make this problem amenable to combinatorial methods. So the way we're going to do this is going to say, okay, any Costas array, remember it has this property that the vectors between any two ones are distinct. But maybe that's not so easy to work with. So instead, what we're going to observe is that a Costas array can never have such a forbidden configuration. So this means that we have these three equally spaced ones which are collinear. Okay, so we have these ones which lie on a diagonal. Okay, so it could of course also be something like this. But the main point is that having this configuration violates the Costas condition because this vector and this vector are the same. Okay, so the idea is if you have a Costas array, it cannot have this kind of configuration. And this is exactly what we can exploit in a probabilistic interpretation of this problem, right? Because we already said that the density that we're interested in, the C of n over n factorial, that's exactly the probability that a random n times n permutation matrix is a Costas array. But by this combinatorial observation here, we know that this random permutation matrix that is a Costas array is not allowed to have any such configuration. So we can just say this probability is upper bounded by the probability that x is 0, where x counts the number of these particular configurations that we want to forbid. Okay, so this way we related the density that we're interested in to this problem here of estimating the probability of this quantity being equal to 0. And so naturally, if you want to prove some exponential decay, you would want to apply some concentration inequality to x. So maybe, because we're dealing here with random permutation matrices, we can think about applying concentration results which apply to random permutations, because from a random permutation you can generate a random permutation matrix. However, it turns out that this is not so easy to handle. There are certain technical difficulties when you want to bound this quantity using concentration inequalities. One problem is that this random variable turns out to be not smooth enough, not really Lipschitz. So in other words, if you apply some transposition to your random permutation matrix, the number of these kind of configurations can change by quite a lot. Actually, we know it can change up to a linear amount, and that is not very pleasant. So to get around this, we are going to apply some trick, some disjoint approximation trick, which can be traced back to this paper by Bolovash. Okay, so what we say is that we know, we're interested in this probability that there are no such configurations at all of this type. These three collinear ones, and so what we're going to say is, okay, if there are no configurations at all, there are also no configurations of a special type. Okay, and so what is the special type that we want to focus on? We want to focus on these configurations which are disjoint. Okay, so we want to count how many such configurations are there where each of these three ones that are equally spaced and collinear, where they all share just different ones. Okay, so this xt is formally the maximum size of a collection of three one configurations of this type that are using disjoint ones. And this has a number of advantages. So in the context of random graphs, counting objects with disjoint edges somehow intuitively gives you more independence. Okay, and in particular, if you want to apply these concentration inequalities like bounded differences inequality and so forth, the point is that if you count disjoint objects, then this random variable will be much smoother. It has a much smaller Lipschitz coefficient. In fact, you can check that if you apply a transposition to a matrix, then the number of these configurations that we're interested in only changes by a constant. Okay. If you want to check the details, I invite you to check the preprint that should be online by the time this conference starts here. And so the point is this random variable is much better behaved than the original one. There's of course a slight caveat that here calculating, for example, the expected value of this random variable is a little bit more complicated. But here also we can use two tricks from probabilistic combinatorics in order to bound the expected number here of this random variable from below. The buzzword here would be that we can use a variant of the so-called alteration method in order to achieve this. And if you want to know more about the details, I invite you to check the draft, which should be on my webpage by now. The main message just is for now here that it's unclear how to directly bound the probability that x is 0 and get an exponential decay. But by using passing on to this auxiliary random variable xt, we make the problem amenable to applying these concentration inequalities for random permutations. Okay, that's really all I wanted to say here in this quick proof sketch. the main open problem I have for you here, and I would really be interested to see some progress on this, is to get some more precise estimates on the number of Costas arrays or the corresponding density, meaning when we renormalize by n factorial the number of n times n permutation matrices. So where are we currently standing? So we prove this upper bound that it's exponential n, and we have this trivial lower bound that's at least n to the minus n for infinitely many n. And so the question really is, can we narrow this gap further? One difficulty here seems to be that, you know, the forbidden configurations that we look at, which are of these three types here, basically, that they're a little bit non-standard for the field. Okay, so there are a lot of results concerning random permutations with forbidden subpatterns. There's this, for example, this famous proof of the Stanley-Wilf conjecture by Marcos and Tardos, but the forbidden configurations looking at, they're more combinatorial in nature. The thing seems to be that these kind of configurations, they have a little bit more geometric flavor, and so some of the established tools and techniques are not available. But I think this is a great opportunity to develop new tools and techniques, or to bring, for example, some ideas from enumerative combinatorics and analytic combinatorics into play in order to get a better handle here on this density, or perhaps even on the number of Costas arrays itself. So if you have any ideas on this or want to chat, please get in touch. I'd really like to see progress on this problem. So let me maybe just briefly summarize what we're looking at. So we're looking at the number of n times n Costas arrays, which is just permutation matrices with constraints. And we showed that the density of these Costas arrays among all n times n permutation matrices decays exponentially. Verifying these speculations go back to the 1980s. And perhaps one interesting twist here was that actually we used in the end tools and tricks from random graph theory in order to prove this result. And I would be really interested to see improved bounds here for the number of Costas arrays. Please let me know if you have any ideas. Thank you very much.